So today what I want to talk about is kind of the core of all of these super recent image generation models, right? So you know about Midjourney and Stable Diffusion and DALL-E 2. The key underlying technology of all that are called diffusion models, right? Denoising diffusion models. And so since we haven't really talked so much yet about the language aspect of things, that's going to come in a couple more weeks. So what we're going to talk about today is, let's suppose, just like you're doing for your homework, that you have a class of objects and you want to learn how to generate examples from that class. Similar goal as for VAEs and for GANs, but diffusion models turned out to be kind of the thing that came out on top in terms of what people are using these days to actually make really photorealistic pictures, or even not photorealistic, sketches and cartoons and so on, right? So basically kind of like the topic of today is what are called denoising diffusion models. And so again, just to remind us, where did we come from, right? So kind of like we started with VAEs, which were probably about like, I don't know, 10 years ago was the hotness, right? Then we kind of started talking about GANs, which was maybe about like 6 years ago. And then diffusion basically came on the scene, I would say around 2020 was kind of like suddenly everything was a diffusion model, right? And so the key innovation of diffusion models was actually about 5 years earlier than that. So basically kind of like the original paper, which I don't think I linked to on the webpage, but basically it was in 2015. And the author was Sol Dickenstein et al. Or Sol Dickstein, sorry. Group from Stanford. And this paper, again, it's one of these things where, not like I'm an expert, but looking at this paper, I would not have thought that this was the paper that would set off this crazy generative AI revolution, because that paper was very theoretical. It kind of links this physicsy concept of non-equilibrium thermodynamics to deep learning, okay? And so, there maybe were some image examples, but it wasn't like you were seeing a paper that had all these DALL-E 2 results in it, right? Then the key paper was basically like summer 2020, which was a paper by Ho et al., largely a group from Berkeley. And this paper was called Denoising Diffusion Probabilistic Models. And so once people saw that paper, then things really started to get rolling. And so let's talk about that paper, right? So for me, the first time I saw this kind of stuff, the idea was incredibly counterintuitive, right? So in case you don't already know, the idea behind all the stuff we're going to talk about today is that you start with a noise image, like a total noisy image, and then through several steps of, less noisy images, as if by magic, that turns into a clear image. And so, if you watch an animation of this, you basically see the image going from noise to clear. And actually, just to steal the thunder and look at the example from the machine downstairs, let's just skip forward a little bit to see what I mean, right? So here's kind of like what the model is doing. Let me just kind of scroll this guy up here. So each of these things starts from like total noise, and then as we learn, that noise slowly resolves into examples of whatever class we are going to generate, right? So in this case, flowers, right? And so it's remarkable, right, to see these clear images emerge from the noise. And so then I thought about it a little bit more, and I was like, well, actually, okay, that doesn't like sound that crazy, because I teach image processing, right? And so image processing, there is this very long-standing problem of denoising, right? So you've got an image that has like kind of grainy noise added to it, and you want to apply something. Like, for example, we're used to applying like a low-pass filter or a median filter to remove different kinds of noise, right? And then the image is clear, right? So this is not a new problem. People have been talking about denoising in that world for a long time, right? The difference is between that and what we're talking about today is that here, it's not like we're trying to go from a total noise image to a totally clear image like in one step, right? We're taking many little incremental steps, making the image less and less noisy every time, right? And that's a more bite-sized problem, right? That makes a little more sense. Like saying, okay, well, I think I could learn, if I gave you an example of a noisy image to which I added a little more noise, could you learn how to undo that little noise? I'm not asking you to go all the way back to the beginning, but just like undo a little bit of noise every time. That seems a little bit more feasible to me, right? And so, again, the way that we do this is that we kind of, start with what's called forward diffusion, right? So forward diffusion is easy, right? We start with a clean image like this. So this is like a clear image. And then gradually we corrupt it with noise until the result is total noise, right? And we do this over a series of time steps. Say we, use like 100 steps, where every time we add a little noise. And add a little more noise, and add a little more noise, right? And eventually what I want is that this image should basically have like zero mean and, identity covariance noise, like IID noise, okay? So if I gave you, this was my problem, right? So let's suppose that this is, x sub 0, and this is x sub t. So if I gave that problem to you, how would you solve it? Well, this is easy. All you do is just keep on adding noise, right? So let's suppose that initially, let's suppose that x0 initially also has zero mean. And actually, I guess I should say here, this is Gaussian IID. So if we initially, kind of scale the input so that, maybe if my total original image is x0 hat, I subtract off the mean and I divide by the standard deviation, right? So let's just suppose we're dealing with a signal right now, not an image, okay? So what I could do is I could say, okay, I take whatever my original signal is and I make it zero mean unit variance. Now, let's just be clear that that input signal x0 is not Gaussian, right? It's got its own distribution, right? But it has these second order statistics, right? Mean and variance. And so what I'm going to do at every time step is I'm going to take my next sample is going to be taking what I had before at time t minus 1 and adding a little bit of noise, right? So this is basically the previous step. And this epsilon t minus 1 is basically Gaussian with, so this is a Gaussian random variable, okay? Same size as x of t minus 1. And this beta is a fraction, right? So this beta here is some number between 0 and 1, okay? And initially, I want beta to be close to 0, right? So what I'm saying is that to get to the next time step, I mostly take what I had before, because this number is going to be close to 1, and I add a little bit of Gaussian noise to it, okay? And so what's going to happen, right? So what is the expected value? And this is, again, good probability review for those of you that took probability with me. So the expected value of this is going to be, 1 minus whatever this beta is times this expected value plus this times the expected value of this. And again, remember that in the first place, if I'm thinking about this inductively, right, my first x0 I rescaled to have zero mean, and the noise I'm adding also has zero mean. So this is going to basically be 0 plus 0 equals 0. So I still have something at zero mean. What is the variance of this guy going to be? Well, remember that variance kind of comes out as the square, right? So if these things are assumed to be independent, the image and the noise, then I'm going to have the expected value of, if I have the means, then this is going to be very straightforward. It's going to be like saying I have the expected value of this squared times, well, actually, maybe I should put this in parentheses, like, yeah. So I can pull the constants out. I get 1 minus beta t times the expected value of this thing squared plus beta t times the expected value of this thing squared. Again, I normalized these things earlier to both be equal to 1, right? So basically, I'm going to get 1 minus beta t plus beta t equals 1. So all I'm basically doing is kind of inductively showing that every xt that I get is still zero mean and unit variance, right? But we should know from probability that as I keep on adding Gaussian variables together, as I keep on adding Gaussian stuff, eventually the Gaussian part is going to overtake whatever the original distribution of x was, and I'm going to get something that's a Gaussian result, right? So maybe you remember from the like central limit theorem, right? If we add a whole bunch of things, well, especially if we add a bunch of Gaussians together, we always have something that's Gaussian, right? The only thing that's not Gaussian in all of this is the very first image, and that first image's influence diminishes over time until basically it's just like I'm adding a whole bunch of noise stuff together, okay? And so as long as this beta is, slightly, as long as this beta is not totally zero, eventually the noise stuff is going to overtake the original image, okay? So let me pause and ask any questions or comments so far. This is easy. All I'm doing is I'm adding a bunch of noise until I get nothing but noise, right? Now, one thing that we could do, right, is that, if I wanted to think about, okay, well, what is happening at the, 58th iteration, right? I should be able to write that 58th iteration as some contribution of the original image plus some contribution of noise, right? So in some sense, for example, let's just take a look at one step of this, right? So if I say x of t is equal to, this fraction of what went before plus some noise, and now I kind of expand this out to say, well, this itself was actually the previous step. Epsilon of t minus 2 plus this thing, epsilon of t minus 1. And I kind of regroup things. I could say, well, there's this part here that depends on x of t minus 2, and there's a part here that is just noise, right? And again, I should know from probability that when I add up these two Gaussian pieces, I'm going to get something else that is Gaussian. And since those are both zero mean unit variance, this part itself is going to be zero mean unit variance, except it's going to be multiplied by some corresponding factors with these betas, right? So kind of the idea is that I can do this inductively and eventually say, well, actually, x of t is something, and I'm going to write it like this, alpha t times x0 plus some other thing, epsilon, which is like saying how much, what is the proportion of original image plus noise, right? And I can write out what the actual values are in terms of the betas, right? So the alpha t is the product of a whole bunch of 1 minus betas, and this epsilon is, basically normal zero identity. And so I can think about this process either as incrementally adding a bunch of noise by means of little increments of beta, or I can think about it as jumping from x of 0 to x of t by taking the original image and adding some bigger Gaussian noise image, right? And so, the kind of like decision about how do I, either the set of betas or kind of equivalently the set of alphas defines what's called the diffusion schedule. Which is just a fancy way of saying how I choose to add noise over time, okay? Okay. So for example, in the original paper, when they were talking about adding the noise, what they did was, original paper, they noised up over 100 time steps, and they said that beta 1 was equal to 0.0001, and beta t was equal to 0.02. Okay? So kind of what they were saying was, in the very beginning, when I've got the crisp, clean image, I add very little noise to it, right? But as the image becomes noisier and noisier, then there's no downside to adding relatively higher variance noise. I kind of am going up by a couple orders of magnitude by the get to the very end, because at that point, it doesn't really matter that much, okay? So, you know, in the early stages, it should be pretty easy to understand how to undo a very small amount of noise added to a clean image, right? And later stages, you know, everything is already pretty noisy. And so you could do this process of adding noise, you know, linearly in terms of how quickly the variance beta changes. You could do it with a different schedule. So for example, let me just go to my picture for a second. So different papers proposed different ways of changing the schedule. And I think that there's a picture of this here. So this is kind of like a picture that shows, you know, how much is contributed by the signal and how much is contributed by the noise over time. If I do kind of a linear offset, this y-axis is showing what proportion of the contribution is coming from the signal. It turns out that if I do this linearly, then the original signal contribution drops off pretty fast over time, right? So that blue curve is coming down pretty fast. Whereas if I were to use like a cosine-based you know, path going from the first noise variance to the last, then there's a little bit more of a gradual roll-off of how quickly the original image contribution falls away, right? And so, you know, different approaches will use different kind of noise schedules. It's kind of a fine point, but, you know, and if I look at how much contribution the noise is making, kind of conversely, if I stuck with the linear schedule, you could see that kind of by, you know, kind of a third of the way through, the noise is really, you know, more than half of what's being added. Whereas if I use a cosine schedule, that noise gets folded in a little bit more gently, right? Okay. So questions or comments on this? So you're saying, where's the neural network, right? So so far there's no neural network. It's just like adding noise, right? But this is the theoretical underpinnings of things, right? So now, here's the neural network, right? Now what we want to do is we want to build a network that reverses this whole process, right? So I start with the noise, and then I get back to the image, okay? So that's the reverse diffusion, right? So we want to, I can't see what I'm writing. So we want to build a neural network that reverses this process. Which is sometimes why you hear this whole thing called reverse diffusion, right? So the idea is that I've got a noisy sample. I want to put it through a neural network, and then I want to get out a little less noisy result. Okay? Or a slightly different way of thinking about this, which is actually what happens under the hood, is that I could think about this x of t, which we know is a contribution of an original image and a noise image, right? I could build a neural network that if I knew where I was in the kind of, you know, process, if I knew what proportion of noise there was, then I could estimate the corresponding noise, right? So this is kind of like the twist of thinking about it, right? This is like saying, okay, I give you the noisy image, and I give you how much noise has been added as a proportion, right? Then can you tell me of that, you know, noisy image, what part is original signal and what part is total noise, right? So this here that I'm estimating should be, you know, like an IID noise image, right? And then if I already knew this and you figured this out, I could undo this equation, right? Because I would know everything here, and I would also know alpha t, so I could kind of revert things to get x0, which would be like the clean image, okay? So that's the critical concept for today, is that I'm trying to predict with a neural network what was the noise that was added to the original image, assuming that I know the denoising, or assuming that I know the noise schedule, I know the alpha, right? And then I can kind of undo the whole process. And so now, again, I'm being a little bit vague about exactly what the structure of the network is. I'll talk about that in just a second. But now the kind of learning target, the loss function for this process, is pretty clear, because I can take a whole bunch of training samples and I can basically look at the loss function as something like do gradient descent. On the difference between the epsilon that I know was added and the epsilon that was predicted by the network, right? So I could do this mean squared error, or sometimes actually you see it just done on the absolute value, the mean absolute error. The nice thing is that everything here is Gaussian, right? So since everything is Gaussian, kind of what I'm doing is, I'm trying to write a loss function that depends on the difference between two distributions, right? The known distribution that was added because I have my training data, and the distribution that's being predicted by the network. Both of those things are Gaussian, and so since both E and E predicted are Gaussian distributions, then the what's called the KL divergence is easy to compute. We talked about this earlier, right? In general, when I'm comparing two PDFs, the difference between those can be a kind of a hairy thing to write, but when everything is Gaussian, it actually reduces to like a super clean formula. Question?
That epsilon predicted, that's the noise that you add to your original image to get to the image that you're at now?
Right, so the epsilon predicted, I'm trying to predict this term here, right? So at the teeth step, I know what the amount of noise is, and I'm trying to predict what was the noise image that was added, right? So this here is kind of like what I'm trying to predict, right? If that makes more sense. Okay. Other questions or comments? Yeah.
Is the model sensitive to the number of times you add the noise?
So the question is the model sensitive to the number of times that you add the noise? And yes, in a way it is, right? So we're going to talk about that in a second. So there's a question about how many time steps do you take to get to the end? And also, as I'll say in a few minutes, we in practice don't actually undo the noise by doing like every single time step. What we'll do instead, as it turns out, is decide on, okay, if I want to get from clean image, or if I want to get from noisy image to clean image, I kind of choose a kind of macro number of steps to get there, and each one of those steps kind of corresponds to a whole bunch of smaller baby steps, right? So yes, all that stuff is kind of like a tunable parameter, and I'll show some results on that in a second. Other questions? Okay, so a couple of key ideas that were in the original paper that were also kind of innovative is, and this is something that maybe if you've read this stuff or read neural network stuff in general, is the network that was used to do this, was something called a U-net. The U-net was originally proposed for a whole different topic. So this U-net paper originally was for biological image segmentation, is where that first idea appeared. And again, if you look back at the page for this lecture, you can see that I believe I put that paper in, right? So this U-nets paper was for Ronenberger et al. In MCAI, which is a medical imaging conference in 2015, right? So again, it's the kind of thing that I don't think that all the vision people were reading this medical imaging journal necessarily, but then it suddenly became like, oh boy, this is actually a pretty good thing to use. One of the reasons that the UNet is good is that it's good for problems in neural networks where you want the input and the output to be images that are the same size, right? So that's kind of why it's good. So it's good in applications where input and output are same-sized images. So, I mean, like, we're used to neural networks, like, especially for things like classification, where the network is maybe taking an image in, and it goes through all this stuff, and eventually what comes out is just a, scalar or something like that, right? Or conversely, where we take a VAE or something like that, where the input is a vector, and we kind of go up to an image, right? So in this case, what we want for diffusion is exactly an input image of a certain dimension, and the output is an output image that's exactly the same dimension, right? Because we're going to be comparing those two things. And so the UNet idea, if I'm going to very sketchily draw the architecture, is the following, right? So I've got a image. This is my input. What I do is I put this image through a bunch of kind of like, and each of these Ds is like a neural network itself, a little mini set of layers that is going to sequentially decrease the resolution. So each of these things is going to decrease the spatial resolution, but also, since these are usually like convolutional neural networks, this is also increasing the number of channels, right? So at every step, what I'm doing is I'm reducing the size of what I've got as input, but I'm also expanding the number of feature channels that I'm getting out of my network, right? And so this goes on for a while. And then at the lowest layer of the network, there are a couple of like residual type blocks. And then to get back to the output, I have a bunch of upsampling network layers. And again, kind of, this is like the inverse, right? So here, I'm increasing the spatial resolution. And I'm decreasing the number of channels until at the very end, I only have the channels that I need to reconstruct the noise image. And what comes out is my predicted noise image. That's the same size as the original. And furthermore, between these corresponding parallel layers, there are some skip connections. Right? So kind of to connect these guys, there are skip connections. And remember, the role of a skip connection is that, if I want to use some information that immediately came out of here, I don't want to have to propagate it all the way through and back up. I can kind of like have a freeway that goes directly between the output of one block and the input to some other block, right? And so that means, and these skip connections are formed between layers that are exactly the same size, right? So it's kind of like everything is kind of equally sized all the way through the network. And there's also like a whole bunch of residual blocks all the way through this network that I'm not really illustrating. One of the reasons it's done this way, and especially, I think we talked in the very beginning about this kind of crash course on deep learning. One of the reasons that these residual blocks and these skip connections are useful is to avoid, we were talking about this vanishing gradient problem, which is basically saying that if I'm taking the gradient over here, it may be a very long path to predict or to propagate some change here all the way through the network back to changes in early layers of the network. And so the learning can be very slow if I don't have these skip connections to kind of like shuttle information back and forth at earlier stages of the network. So that was something that was very useful for making this denoising diffusion model perform well in practice. Another thing that was really important was this kind of concept called attention. Okay, and so at this point in the lecture, I don't want to like launch in on attention because attention is a big concept, right? So I will talk about attention in detail when we talk about language models. So I'm just going to put a pin on it that says that, you know, one important thing about attention I want to talk about now is this is going to be a key concept for later. For example, in language models, attention is super important. But the main thing I want to draw from attention for this lecture is that one thing that we're doing in this network that we haven't done before is that the input to the network is kind of like not only this input image, but also this scalar number, right? And so kind of a key idea is, you know, how do we make that influence of that scalar, you know, have sizable influence on what the network does, right? Because otherwise you can imagine that if there were like millions of parameters in a 1024 by 24 image and there's one number for the alpha, you know, how am I going to make that alpha play the same role as the image? Because the alpha is really important because I have to know how much noise did I add to undo the noise, right? So the question is, how do I, you know, make the influence of that scalar felt in the network, okay? So, you know, the key kind of idea is to, you know, convert a scalar input, you know, which is here, this alpha, into a more complex representation that the network can usefully work with. Man, my writing is bad today, I'm sorry. So the idea is we want this alpha to really have an impact on the network. And so the popular way of doing this, which has kind of become the de facto way of doing it, is using what's called an embedding, right? So we talked already a little bit about the concept of an embedding in the world of like, you know, VAEs and GANs and stuff like that. But there's a very particular embedding that has become popular for kind of going from a scalar to some other dimension embedding, right? And so the key idea is what's called a sinusoidal embedding. So popular method is what's called sinusoidal embedding. So the idea is to turn a scalar t into a vector, or more generally a matrix of length L. And so the way this is typically done is very simple, right? So t is a scalar, right? What I do is I make a vector, and the entries of that vector are a bunch of sines and cosines of various frequencies. And so I know that at least a chunk of the class here came out of like the signals and systems world and our other, you know, kind of ECSE curriculum, right? So this should remind you a little bit of like a, you know, Fourier series or a Fourier transform, right? And it is like that, right? So what I do is I have an increasing set of frequencies omega 1 through omega L over 2. So I'll say a little bit about that in just a second, but like this in some sense is kind of like saying I have a set of sinusoids going from low to high frequency, and I take my value t and I evaluate where those sinusoids are at point t for all the sinusoids that I have, right? In practice, what actually happens, I don't think it matters that much, is that the sines are all at the top of the vector and the cosines are all at the bottom of the vector, so they're not interleaved like I drew it here, but it doesn't really matter that much, right? And the frequencies are chosen to not be linearly progressing. Basically, they are set to be like, in the original paper, the proposal was this, 2 pi times 10,000, and this is like a really, you know, magic formula. The idea was that, for example, if I plug in omega 1, I have, 2 pi as the first frequency, and omega, the last omega, is 20,000 pi. And the increase from the omega 1 to the last omega is definitely nonlinear, right? So I'm not like spacing these out linearly. I'm, spraying them out in kind of a logarithmic or exponential way, right? And so the result of that is, well, first of all, the other thing I'm going to say is that, the mapping between the scalar and the set of sinusoids is unique, right? So there's kind of like a one-to-one mapping between a given vector and a given t, right? Those two representations are in some way equivalent. I mean, certainly the vector is like way over parameterized, right? But that's kind of the point. The idea is that, I can go from any length, I can customize the length of that vector to be whatever I want, and things will still be unique, okay? And here's kind of a picture of that, or maybe I should, well, I can look at the picture. Hold on a second. So here's kind of a picture of, kind of hard to explain, but more or less the first chunk, if I'm trying to embed a single number into a 32-dimensional vector, right? Kind of what I'm reading off is that the top part of this matrix are like the sines, and the bottom part of this matrix are like the cosines. And as the noise variance changes from 0 to 1, I get a different pattern in each column of, basically samples of sines and cosines. And so it's like saying that every column of this long matrix is a unique representation. And you kind of can see, visually like these little kind of curvy or, cosine-looking things that are inside this embedding, right? So kind of what's happening is every time I choose a noise variance, I kind of have a lookup table of what should my corresponding vector be, okay? And so you can see that that's just a one element, piece of code in this sinusoidal embedding, right? Where I basically am saying, what is my number and how many vector lengths do I want, right? And so this idea of embedding a number into the neural network is going to become, as a flash forward, very important when we talk about things like large language models, where I want to have my network paying attention to different words previously in the generated output or in the sentence that I asked the thing to respond to, right? So for example, if I say, a panda wearing a hat, I want to have different elements of the network responding to panda and hat and so on, right? And the positions of the words in the prompt are going to end up being embedded in this kind of sinusoidal embedding, right? So that's going to be something that comes into play when we start talking about like transformers and ChatGPT and so on, okay? And so just to, well, okay, let me pause and ask questions or comments about this kind of idea. Okay. One thing I will say, just to be clear, is that since in the UNet, I'm trying to kind of like predict things that are image sized, in practice what happens is that it looks a little bit more like this, where I have, in our case, the input to the UNet is something like, I have my image. So let's suppose that this image starts off as like a RGB 64 by 64 image, okay? And then I have my alpha t, which is a 1-by-1 scalar, right? So we just learned about how I could embed this 1-by-1 scalar into a vector. So say I turn this into like a 1-by-1 by 32 vector. And then what I could do if I wanted to make this look more like a matrix is I could just, upsample this whole thing into a 64 by 64 by 32 tensor, right? So all I'm doing here is I'm just copying that vector into each of those 64 by 64 slots, right? At the same time, I could put this image part here into some sort of a convolutional network that results in an image that has like 64 by 64 by 32 channels. Now these things are the same size, and I can concatenate these two things into a 64 by 64 by 64 tensor, and then that goes into my whole UNet process, right? Question?
So given this scheme, so
Mhm.
when you use this Sinusoidal embedding, like at each given t, the alpha
Mhm.
t, so the effect of this positional embedding will be the same along all the spatial dimension, right? Because you simply just have
Because I'm copying like this, right?
Yeah.
Yeah. As far as I know, yeah. That's my understanding of how the alpha t comes into the network, yeah.
Yeah, because I remember like in the VIT for the MAE, like
Mhm.
they usually use the sine on the x dimension and the cosine on the y dimension, so that they will have like.
Oh, I see. Right. So there may be different ways of doing the embedding to get to the matrix other than like this picture and copying, right? So what you're saying is that what I could do is I could take the top half of this matrix and the bottom half of this matrix and think about like a product or something like that, right? To make a 2D image directly from that, right? Yeah, I guess you could do that too, right? I think that people have definitely changed their thinking about exactly how to do the embedding. So maybe that's the modern way of doing it with a visual transformer, right? Yeah, could be, right? But yeah, it's a good point, right? Okay, so let me pause and ask. So questions or comments about this? Okay, so now we basically train this whole model, right? So what I'm doing is I'm training the model to denoise. So in some sense, like I've got these two parameters, right? I've got the input image and I've got how much noise there is. And I've got lots of examples because I have the ability to do forward diffusion on whatever images I want, right? So in practice, what I would say is I have my class of flowers or cats or Legos or plants or whatever, right? And I can, arbitrarily create as much train data as I want of the noisy versions of those things, right? So the hope is that when I do the forward diffusion process, even though to the human eye, all those output noise images will look basically like TV static, the hope is that those noise images do in fact contain a germ of the original Legos or plants or flowers or whatever, and I'm training a network that is specifically tuned to denoising things to make pictures of Legos, right? Like it's not going to be something that will work for every type of input image. It's kind of tuned to the class that it was trained on, right? Until we start talking about the bigger picture models, where we're kind of fixing ourselves to this one class, right? And so now let's talk about how to get the image back again, right? So this kind of goes back to the question that was asked before. So we train the model. And now, how to get the image back again. Well, we're not going to predict x0 from the noisiest noise image in one shot, right? I mean, in theory, we know via the alpha and our noising schedule how much noise was added, but in practice, it's not going to work very well if we go in one shot, right? Conversely, I don't want to have to take 1,000 baby steps from the noise image to the original image, because in some sense, that means I'm applying the neural network explicitly every step I take, right? And every step is going to linearly contribute to how long it takes to generate the image. And so if and this is obviously an engineering trade-off, right? So certainly, I think that when they released DALL-E 2, I don't know whether it was explicit, but I think it was pretty clear that you were going to get your image in whatever it was, 15 seconds or 30 seconds, right? So they don't want their denoising steps to take 2 minutes. No one's going to wait around for that, right? And so in practice, even if this original t is big, we get from xt, which is super noisy, to x0 in fewer steps. Like maybe we do this in like 20 steps instead of 1,000 steps. And so how does that work, right? So the idea is that, we first predict epsilon t from xt to estimate x0, right? This would be the equivalent of like going all the way to the beginning in one step, right? Obviously, this is going to be a pretty poor estimate of x0. But then the next step is that I reapply this noise, but only over, t minus 1 time steps to estimate x of t minus 1, right? So in some sense, it's like saying, if I draw this slightly differently, it's kind of like saying, okay, I'm going to start with xt, and I'm going to initially estimate the original image. This will probably look like crap, right? But I don't care, because then I'm going to apply, noise to get me just like a couple clicks back from this, right? So it's okay if this, image is poor, because I'm just going to add lots of noise back to it to get to here, right? And then I kind of keep on doing this seesawing back and forth, right? So basically, the number of discrete steps I take, and I guess I'm being a little bit hand-wavy about what t means here, right? The number of discrete steps I take here may be like 20, even though the model may be taking, 980 steps to get from here to here. I'm actually kind of like bunny hopping over a lot of explicit steps, right? And then the other thing that's kind of cool about this is that, as I've described this, right, there is nothing that is, even though this whole lecture has been about noise, right, the way I've described it, there is nothing actually non-deterministic about the network, right? So once I train the network will always give me the same estimate of epsilon t for a given input x and a given alpha, right? There's no uncertainty in what the network will do, right? So if I want a little bit of uncertainty, basically I can add a little random noise, additional noise, at this step if we don't want the output to be, entirely deterministic. Right? So we all know that when we generate something from DALL-E or from Midjourney, that you can get usually 4 example images that all look slightly different from the same prompt. And the way that's working is that basically, when I do this step, I can interject some noise here that's going to, throw things off a little bit, so that when I keep on undoing it, I'm not going to get the same x0 every time, right? That part is something the network doesn't know what's going on, right? There's something that's uncertain to the network, right? And so this is also basically what's happening when you make a Midjourney result and you say, hey, I like image number 3, show me variations on that theme, right? The same kind of thing is happening where I'm interjecting some random noise at some point during the denoising network to give a little bit of change in what the resulting image looks like, right? And so this is kind of like the progenitor of that like 2x2 array of options that you typically see in these image generation things, right? And so, obviously, the more steps I take, the better, right? So, I mean, if I wanted to make the best possible image that I could, I should be taking baby steps all the way back to x0, right? But from a kind of engineering real-world point of view, I can't afford for the user to wait to take these 1,000 steps, right? So there is a tuning aspect of how many steps should I take. And so you can look at the notebook. So what I'm showing you here is exactly the notebook that came from class, or came from the book, right? So here, here it is, like build the UNet, blah, blah, blah. And so here is an example of, the epochs of training. You can see that the flower data set slowly emerges out of training until the results, even after like 10 epochs out of 50, things already look pretty good. And when I do inference, that is when I draw from the network, you can see that there's this parameter that says diffusion steps equals 20, right? That's like specifying how many steps do I want to take along the way from the noise image back to the original image, right? And these generated images, they look very good, right? They look sharp, they look realistic. And this matrix is kind of like an illustration of what would happen. Unfortunately, these are not labeled, but basically it's like saying, instead of taking 20 steps, what would happen if I took, 100 steps or 120 or 200 steps or whatever, right? So in the beginning, this is like saying, I think the top row is like saying, if I only took like one step all the way from x of t back to x of 0, what would that look like? The resulting image would look pretty poor, right? I mean, it's already pretty like interesting in the sense that starting from a random noise image, if I only take like a huge step back to x0, I'm already getting qualitatively, colored blob, flowery looking things, right? And if I up my number of steps, at some point there's a period of diminishing returns, right? So here, the bottom image, I think, is what happens if I literally take baby steps all the way back from x of t to x0. But if I were to take substantially fewer steps, that's probably what this row is, I get images that are visually pretty much the same, right? And so this is an engineering trade-off of how many steps should I take. And that's something that might be worth playing with your diffusion model, right? To see how many steps should I take to get back to the original image, right? And just like VAEs and GANs, you can do all the same kind of latent space arithmetic that you did before, right? So what you could do is you could take two original, source images, find out, you noise them up, add those noises together and undo the image in the middle with different, fractions to get these kind of, steps from one thing to the other. And so the latent space arithmetic kind of operates in the same way that it would for like a VAE or a GAN, right? And so I'm hoping that you guys should be able to train your VAE, or not, sorry, your same data set, both using diffusion and using GAN. And I think that, honestly, I'm hoping that the diffusion training process will be very smooth and be a lot less prone to convergence issues and tuning and so on than for the GANs. Has anyone actually tried this yet on their data? All right, well, you have a weekend plan then, right? So has anyone tried tuning the GANs yet on their data? And how is that part going?
I don't get the results, but the completion was fine because I use the style GAN, so more evaluation.
Okay, and you guys are having good results on your GAN, right? So yes, I'm looking forward to seeing how it works. I mean, like I said, for the generator discriminator, you've got these two networks you have to train, you have to balance like how many generator steps you take before you take a discriminator step. There's lots of stuff to tune in GAN training. With diffusion training, I don't think there are that many choices to make under the hood of how the model should work, right? I guess you have to make some choices about like resolution and how deep your UNet should be and whatnot. But I think that, honestly, I would be surprised if adapting this notebook from the book doesn't already give you, hopefully, pretty good results, right? And I think there are also probably some pretty good off-the-shelf diffusion models that you could use as well. So like I said, so now we've kind of covered the critical milestones from VAEs to GANs to diffusion models, right? There is one more little thing I want to talk about after next week, which is normalizing flow models, which is something that I always thought was kind of cute. I mean, I don't think it's necessarily like on the critical path, but I do want to just mention it. In fact, that lecture will be probably on the shorter side. So I'm expecting that probably you're going to submit your homework on Thursday, right? And then I'm going to see what you submitted over the weekend. And probably on the following Monday, I'll do a short lecture on normalizing flows, and we can take a look at what people were able to get out of their GANs and diffusion models. And then after that lecture, I guess it's easiest to just look at the actual browser, right? So after that lecture, we go back to the syllabus, and then we're going to do language models, right? So basically, we're going to spend 3 lectures that are mostly or entirely on words and sentences, and then we're going to talk about CLIP, which is going to be the connection between words and images, and then we have a couple lectures on back to diffusion models, right? So one lecture on how does DALL-E 2 and stable diffusion actually, do its job. And then there are all sorts of crazy extensions of diffusion models, like you may have heard of ControlNet or Dream Booth. You know, we're going to kind of like have a lecture that comes back to all the stuff that people have been doing with diffusion lately. And then we'll basically have covered, you know, that's 3/4 of the way through the semester, right? So we'll cover almost everything I wanted to talk about. And then I will talk about a few things, like we'll talk about generative models for music, generative models for making 3D things, and then kind of a catch-all, like people apply generative models to all sorts of crazy things. So I want to do a kind of like a big picture of like what else has been generated that isn't just like audio-visual stuff. And then that will be the end of the class. Okay, so comments or questions? Yes, question?
Will be homework throughout all that?
Yes, there will be homeworks. I have to write the homeworks. So basically, I need to work on that over the next week. So I think that there'll be homework 3 will be on language model stuff, I imagine. Homework 4, I think, will be on what cool stuff can you do with stable diffusion. And then homework 5 will probably be on, you know, make your own nerf and see if maybe you could make some simple music or something like that. That's kind of what I'm thinking. So in particular, one thing that you might think about, I don't think you're not going to need it for homework 2, but it might not be a bad idea to, we'll talk about, you know, stable diffusion, right? But you could already start putting stable diffusion on one of your high power machines and playing around with it, right? Because stable diffusion is the only open source diffusion thing. And of course, that's responsible for all of the really community driven crazy stuff that people have been able to do, right? So all of this low rank approximation stuff and so on, like there are lots of things that are built into, you know, the stable diffusion releases. And of course, you can always use DALL-E 2 and Midjourney, but you can't get under the hood of those in the same way that you can with stable diffusion. Cool. All right, other questions or comments? Yes?
So in the homework you mentioned like which generates certain examples by some diffusion or latent space. So latent space actually is in single noise, right? So it wasn't even come back.
Right, so the latent space in this case is the noise image that goes into the unit, right? Yeah. So yeah, I guess I should have been more explicit. So yes, the latent space here is just this total noise image. Yeah. Right, I'm going to stop my lecture.